we have now the ratio of two quadratic forms, and we want to know for what values of L is that ratio of quadratic forms greater than or less than 1. And we know from linear algebra that the roots of the two quadratic forms are going to be determinative in identifying whether or not it's less than or equal to 1. However, what's the Cauchy-Schwarz inequality? Anybody remember? If you have two vectors, the inner product of the two vectors is always less than or equal to the product of the length of the two vectors. So by the Cauchy-Schwarz inequality, we know that this ratio can never be bigger than this. That said, here we have sigma squared in the denominator. Suppose I'm estimating that, and I have beta and beta here. Those are my parameter vectors. Suppose I'm estimating those. What does that thing look like? What kind of statistics does that look like? I have a sum of squares in the numerator and a sum of squares in the denominator, and that has what kind of distribution? Ratio of two chi-squares. There's a sum of squares in the numerator and a sum of squares in the denominator. My sum of squares, if I'm having sigma hat squared here, I'm dividing by the degrees of freedom. The only thing missing would be j, which would be the number of restrictions that is in the numerator. So that's by way of motivating that I can use my garden variety F statistic to test the hypothesis that the mean square errors differ from one another. However, now comes the wrinkle. Over here, under the null hypothesis, my F statistic is a central F. That is to say, after I get finished constructing the F statistic, under the null hypothesis, the two chi-squares that I used, both are constructed from normal 0, 1 random variables. However, I just got finished saying we're interested in looking at Q, where we're willing to accept the fact that this null hypothesis is not identically true. It could be a little bit wrong. So if it's a little bit wrong, my garden variety F statistic under the null hypothesis is no longer a central F. And in fact, when my null hypothesis is that when my null and alternate are stated that way, then I've agreed beforehand that the F statistic that I conventionally construct is not constructed from central chi-squares, because they're not constructed by from normal 0, 1 random variables. Because I said, I don't know if this is exactly true. It probably isn't. And so I'm not centering the normal random variable from which I construct the ratio of chi-squares on a normal that has a 0 mean. It's somewhere else. So my regular F statistic, it turns out, has this as its non-centrality parameter. So testing this null hypothesis turns out to be equivalent to testing a hypothesis about the non-centrality parameter. I can estimate the non-centrality parameter and test the hypothesis that it's 0. If the non-centrality parameter is 0, then there's no harm in imposing my restrictions. If I reject it, then my restrictions did some harm. So what I want to do is use my F statistic, and I'm going to look up critical values from an F table where the non-centrality parameter that I use is determined by the data. A non-central F looks like a regular F. It's just pushed off to the right a little bit. So given a critical value, there's more area in the upper tail for a non-central F, or more area of the upper tail is pushed off to the right. So under the null hypothesis, the non-centrality parameter that we're going to use, that we estimate by our model, can be as big as a half, and we would still conclude that restricted least squares is good. So the way we construct the test is we decide a level on which we want to conduct the test, like 10%. We construct a lambda hat, we construct our garden variety F test, and we get out a set of F tables with a non-centrality parameter of a half, because we know that for sure, if OLS is better, it's going to belong to a distribution that has a non-centrality parameter smaller than a half. If OLS is worse, then it belongs to a distribution where the non-centrality parameter is greater than a half. So we pick a half as the non-centrality parameter that we're going to use. So where do you find non-central F tables? Are they in the back of the green? No. Instead, you can go there on my website, down here where it says probability calculator, go there, go to doubly non-central F. And so, for example, if we had, I don't know if it still works, I did this years ago. Suppose the number of degrees of freedom in the numerator was 3, and the degrees of freedom in the denominator was 12. The numerator non-centrality parameter is, let's make it a half, 0.5. The denominator non-centrality parameter, under the alternate hypothesis, the most general model, the non-centrality parameter in an F statistic is always 0. It's very rare. We'll talk about another case tonight where it's not. Okay, but that's a very special case. And we could look for, we'll look at the area above the critical point, and, the F below that. So for the central F, the probability below the critical point is 0.73, 0.74. But for the non-central F, because it got pushed off to the right, the area below the critical value is only 0.68. Okay, so there's less area in the lower tail when we push the probability distribution off to the right. So that means that we're less likely to reject a true null when we're using mean square error as our criteria. So what were we comparing? Mean square error, what we talked about at the beginning. We said mean square error was the expected value of beta hat minus beta post-multiplied by beta hat minus beta transpose. That was our definition of mean square error. And we get a result that's k by k. Maybe, instead of trying to make that k times k minus 1 over 2 set of comparisons, maybe there's a different comparison we could use. We could change the stringency of the test. We might want to base our test on the distance between the truth and our guess. Instead of looking at all the variances and covariances and all the biases and their cross products, let's just look at the notion of Euclidean difference. So instead, we're interested in the expected value of the squared difference between our least squares estimator and the truth and our restricted estimator and the truth. When we define risk that way, that just turns out to be the trace of mean square error. So in F-test, we were looking at our null hypothesis was that our restrictions were identically true. With the mean square error test, we said we're willing to trade off a little bit of bias for some variance, reduction in variance. In the usual F-test, all we looked at was variance. Now we're making a trade-off between bias and variance. And now we're interested in the k-dimensional distance between our point estimates and the truth. And that's less stringent still than even mean square error. So since this definition of risk in the Euclidean distance, using Euclidean distance is just the trace of the mean square errors, we'll look at that instead. And the trace is positive, meaning that our restrictions are better only if, for our garden variety, this is a long, very difficult proof. It's in the Journal of Econometrics decades ago. Only if the non-centrality parameter in our usual F-test is smaller than this other thing. Okay, so you know S, you know R because you designed it. S is given by the data, and G is the characteristic root out of the part and square brackets. So we use that for our non-centrality parameter, driven by the data. We pick a critical value out of that table, and then compare our usually constructed F statistic with a critical value out of that non-central F. So for any given level of the test, any given significance level, our critical value is quite small for the garden variety F-test. It's bigger for the mean square error test, and it's bigger yet for this risk-based test. Okay, so we're becoming less and less stringent with these different versions of the F-test.
Is lambda the non-centrality parameter?
Yes. Yep.
So lambda star, what does the star indicate?
I just thought it looked naked without a character on it.